So what I'd like to do is we're on page 1. We are going to do 1 or 2 of the pre-lab queries. It says we're going to start with number 1. You've just made yourself a cup of hot tea or hot coffee and you get called away for 15 minutes. What happens to the coffee or tea during that time? Uh, I will fill in the answer for that. It cools down. But what I really want to know is why. And so I'm seeking answers from students. Does anybody have one for me? Why does coffee or tea cool down over time?
Is this something we should already know, like from other labs or? Um,
So no, it's just yeah, yeah, no. So you may or may not know it, but I mean, I guess so. First, let me just verify. So everybody's familiar with this idea that it cools down. Is that true?
yeah, that's
Yeah. Well, I guess let me start with this. Then let me continue with this question. Then, where does the heat go?
in, in the air to the surroundings.
Yeah, no, I mean it does. It does. It goes into the air. It goes into the surroundings. It and so uh, yeah. I mean it's interesting to think about because it's something that we're familiar with every day. I mean every day my coffee cools down, uh, and not every day do I get called away for 15 minutes, but when I do, my coffee's cold when I come back. Or um, but yeah. So the answer is why is that the heat, I mean, a good word is dissipates or spreads out. So heat spreads out or dissipates.
We can see your paper, sir.
Yes, that's okay. So write down your own version of the answer for now. If there's a time when I show my page, it'll be later. So you're writing down your own answer. Fair enough, though. I do usually show my paper. So the answer for why, though, will be heat spreads out or dissipates. Antonio and Mary. So Mary, it does go to the surroundings. That's another way to say the answer. And because the air around it is colder, yes. And so, and this is something we are familiar with in our calculations from this class, but over time, so basically everything in the room you're in or everything in the room I'm in is going to come to the temperature of the room, right? And that's our experience. Uh, if you have something hot in a room, it will cool down. If you take an ice cube or cold water out of a refrigerator, it will come to room temperature. So, yes, energy is lost to the surroundings. But I want to say a little more than that. Although that's a fine answer for this question. But the idea is that it is lost to the surroundings, but the energy is still there, right? So energy is neither created nor destroyed. It does move. And then your question is, well, if that heat goes into the room, then why isn't the room hotter? And the answer is maybe it is a tiny bit hotter, but then your room exchanges heat with the next room, and then eventually, our house was built in 1960, and so there are small gaps everywhere, and so eventually the heat makes it outside of the house. um, yeah, it moves. um,
Does this have anything to do with those, I guess, molecules? How you like in a liquid, and how they're closely packed together and moving around and all that. Do they like slow down a bit as they get colder, or are they just kind of?
Michael, you're right on. So yes, so they do slow. So whenever something becomes colder, whether it's a liquid or a solid or a gas, it has less kinetic energy. And we know that as a gas, it's flying around at hundreds of meters per second. And so if it cools down, it will slow down a little bit. And the same thing is true for a liquid. So it loses kinetic energy, and so it's only moving like this, and then it slows down a little bit more. And for a solid, which is vibrating in place, it's vibrating a little more slowly. So all those things are true regardless of the phase. Yeah, so I mean, as far as your answers for that, as long as you say something like it cools down and that the reason why is any of those things, energy spreads out because the air around it is colder. And then I guess the temperatures. So something hot and something cold come to a medium temperature. Something in there. Any questions about that one? What is the situation when it is an enclosed container? Good question. So the short answer is, or I don't know if this is going to be a short answer, but let's try it. So there is no such thing as a truly enclosed container, or let's say this, it's very hard to make because if you think about, so I have one of those insulated carafes. Actually, I have one right here. And I pour my coffee into it every morning, and it says it's insulated. And insulated is a way of saying that heat it can't really, it's not very easy for heat or energy to get in and out of this thing. But after an hour, my coffee is cold, or much colder than it was anyway. So is it, like, the first thing I would say, is there anything left in there? I might have to drink it. Is, it's very hard to do. And so the best thing you can do, there's a little more coffee in there. The best thing you can do is you can create like a container that only leaks energy very slowly, right? And so if you do your experiment over 2 minutes, maybe it won't lose any significant amount of heat over those 2 minutes or 5 minutes, because over an hour or over 2 hours, it's really hard to keep things. So, but what we can do is we can actually do an experiment over 1 or 2 minutes or 5 minutes, and then assume that so little energy has been radiated or moved away that essentially it's constant. But yeah, but energy is always moving. Yeah. So the time makes a big difference. And so we're going to watch some videos later on where the experiment takes, so say 5 or so minutes, 5 to 10 minutes, and we will assume that no energy leaves the experiment. But that's not perfect. It won't, and if we did this lab face to face, we would assume that no energy leaves, but that's not a perfect assumption. And it's very hard to do. And in fact, what if we were doing this scientifically, like completely scientifically, what you do is you actually heat something up, and then you watch it come back to room temperature, and you actually figure out the constant rate of energy leaving, and then you subtract it off your experiment, right? Because there's always some energy leaving, and so you just account for it, which is pretty cool. Anyway, good questions. Now, A, would you call this a physical or a chemical change? Before you answer, so I don't know if I've covered that in this class, so let me cover it first, and then of course the answer will be maybe obvious. I don't know. Let's see. So a physical change, let's start with a chemical change. A chemical change is a chemical reaction. And that's what I'm writing down. A chemical change is a chemical reaction in which bonds are made, bonds are broken, or both. A chemical change is a chemical reaction in which bonds are made, bonds are broken, or both. And so when coffee, or let's just say it's hot water, so when hot water cools down, you have hot H2O and you have cold H2O, and so no bonds were broken. The temperature changed, but the cooling down is a physical change. So for A, and we're not going to answer B, so you can use that space too. It is a physical change because no bonds were broken. It is a physical change because no bonds were broken. And that's a fine answer. If you wanted to add to that, you might say the temperature of the coffee changed, or the temperature changed. That's it. And yeah, go ahead.
Would it be correct in saying, going back to what I had said just a moment ago, that the particles are not, they're not technically like a chemical. They're technically physical. You can't see them, but they're, I don't know, like maybe I'm not describing it correctly, but that's how, when I first read the question, that's where my mind went to, in terms of when it, as it cools down, I said, oh, when things are slowing down, the energy's still there, the molecules are still moving around, they're still tightly close back together, but it's just slowing down a bit. And I thought maybe in terms of describing whether it's a chemical or physical change, my mind immediately went to physical, because I just thought, well, they're physical themselves, the things that are moving around very fast.
Yeah, no, I mean, so I think, Michael, that's a good way to think of it, because you're actually like, it's more like a physics problem than a chemistry problem, because you have the water and it's changing speed. So I think that if that's a good way, like, I think we have a lot of intuition about these things, and so use it. Yeah. So, but yeah, you're right. It is a physical change because it's a physical process, um, And so one of the other things that's kind of hard, so is that you'll ask for for a physical change, is what happens when ice melts. And that's a little tougher, because it's going from H2O solid to H2O gas. But you'll notice that no bonds are breaking, meaning you have H2O at the beginning and you have H2O at the end. So it's a physical change. I don't know, like if you're ever asked the question in this class, and you probably won't be, but if you were, and somebody said, is it a physical or a chemical change? Think about, do you have like different chemical formulas from the beginning to the end? And anyway, I don't know if that helps, Michael, but I think you've got it. What we're going to do is we're just going to skip number 2, so put a big X through it, and we're going to turn over to page number 2. And I will read through the introduction. So you've experienced the exchange of heat energy in physical and chemical systems in the laboratory and in your personal life. And from what you know, which way does heat flow? And so I'm going to chime in here because you think of it, I think, as moving from hot to cold or cold to hot. But I think this is a trick question because whenever there's something cold and whenever there's something hot, they're basically flowing towards each other. You might say, well, the hotter one is moving faster, but typically they're all just mixing. So we're going to skip that question too. And generally, we say that heat energy flows from a warmer object to a colder object, but that's generally what we say. And it basically answers the questions that we've talked about before. And so now we're going to actually move down to part 1, heat transfer in a physical system. In this part, you will be studying heat transfer between a metal cylinder and water. The cylinder will be heated in boiling water and then placed in room temperature water. And what will happen when you put the hot cylinder into the colder water? How can you monitor the amount of heat transferred? Well, we're going to watch this. 2, will the amount of heat exchange be the same if the identical hot cylinders are placed in different amounts of water? So we're going to actually come back to question 2. We're going to skip question 1. And so think about question 2 and take a minute and read over all of the questions that we're going to be going through as you watch the lab. I think I've put them in order. I did this about 6 months ago in the spring. So let's try and answer them together. Or let's see, answer them while you watch the video, and I will do my best to stop it and give you time to answer. But I have to share my screen, I know. Otherwise, I just watch the video. All right. So let me go ahead and start.
Now we're going to look at the specific heat. Specific heat is defined as the amount of heat required to raise 1 gram of a substance, 1 degree Celsius.
Stop there, answer the first question. Let me play it again.
Defined as the amount of heat required to raise 1 gram of a substance, 1 degree Celsius.
I can replay these parts later, but for now I'm going to move on.
For example, water has a specific heat of 4.184 joules per gram per Celsius degree. We have a piece of cadmium metal.
Go ahead and answer question B. And question B is something that is on your conversion and equation sheet anyway, and it's probably something you're pretty familiar with. And go ahead and answer question C with its chemical symbol if you would like. It's on the screen now.
Metal. And we're going to try to find out the specific heat of this metal. We know that the quantity of heat is equal to mass times the specific heat times the change in temperature. So let's start by finding.
Sorry, I can't see the chat, so I'm going to check the chat. So I think these are old questions in the chat. I can tackle them later if you still have them. Let's get back to the video. And I'll replay that last part.
We know that the quantity of heat is equal to mass times the specific heat times the change in temperature. So let's start by finding the mass of our sample.
I'll give you a minute to make sure you've answered D. And as you answer question E, it'll show up on the screen in a minute. And when you see it, so you can just write it down. You can put it in your data table later. If you have time to put in your data table, that's fine.
The mass of our sample is 58.953 grams. What we're going to do is we're going to heat this sample to 100 degrees, or approximately 100 degrees. We'll get the exact temperature. And we're going to take 100 milliliters of water at room temperature. So let's measure 100 milliliters of water. Remember that 1 milliliter of water is 1 gram. So if we know that we have 100 milliliters, then we know that we have 100 grams.
Go ahead and answer letter F.
And this is at room temperature. So we know that when we put this hot metal in there, it's going to gain heat. We're going to use our coffee cup calorimeter because it's insulated. And we're going to assume that it gains no heat. And the water...
So did you hear why we use a styrofoam coffee cup? What's the one word that they used?
It's insulated.
Insulated, yes. Oh, and thank you. Now, you don't see styrofoam coffee cups too much anymore, or at least less than you used to, because of the environmental hazards of styrofoam. But if you've ever had a styrofoam cup versus one of those paper cups that like they have at most places now, you may remember or you may know that styrofoam is a much better insulator than paper. And that's because styrofoam is basically puffed plastic. It's got lots of air in it. And that air acts, so the air actually acts as an insulator. What is, yes.
Water gains all of the energy that's given off by our metal. So let's find the temperature of our water. And the temperature is 22 degrees.
Go ahead and answer H.
Celsius. And we have our water boiling, so we're going to tie a string to our sample so that it doesn't touch the bottom of the beaker. If it touches the bottom of the beaker, then we don't know for sure what the temperature is. But if it stays in the water, then we know that the metal will be the same temperature as the water temperature.
All right, go ahead and answer I. It says, why is it important to suspend the metal in the middle of the water? I will go ahead and answer this one. So the metal is at the same temperature as the water. I'll say that again. So the metal is at the same temperature as the water. And that's a fine answer. And what was not really said, but if I was going to answer the question, well, what else would it be the same temperature as? If you place it on the bottom, then because the bottom is hotter, because it's on the hot plate, it would be hotter than the temperature. And if it was near the surface, so it may have an influence of the air above it, and the air above it is at room temperature. So the idea is you have to suspend it in the middle of the hot water. I will tell you, practically speaking, suspending a piece of metal in a glass beaker is a recipe for breaking the beaker and spreading hot water all over the place. And so were we to do this lab, we would just place it, I don't know how we do this. Oh, you know what we usually do? We usually place an insulating layer inside the beaker so that, and then just rest it in the beaker. Usually we use aluminum foil when I've done this before, because the aluminum foil absorbs any possible breakage or clanging of the metal into the glass. Let's continue.
Let's put our thermometer in the water, about the same height, and then we'll lower everything in the water together. Okay, and we're going to let this boil long enough that we know that the temperature of the metal is the same temperature as the water. I think we've waited long enough to be confident that our metal and our water are at the same temperature. Our temperature is exactly 100 degrees.
Exactly 100 degrees. In fact, 100.0 degrees. That's the answer for letter J.
So I'm going to take out my thermometer, and I'm going to take my sample, and I'm going to quickly put it in the water. Put the top on, swirl it around, and we're going to swirl the cadmium metal in the water with a thermometer to try to make sure that we get uniform temperature. We'll read our thermometer, and when it stops changing, we'll record that temperature. And it looks like it's steady at 25 degrees C. So that means...
Let's go ahead. Well, I think, yeah. So let's do L, which looks like a number 1. 25.0 degrees C. And then question, what was J one more time? J was 100.0 degrees.
Please, what was C and F? I missed that part.
So C was CD, as in cadmium. And F was 100 grams, because it was 100 milliliters of water.
Thank you.
Yep.
means we have a 3-degree temperature change. So you now have the temperature change in the water, the temperature change in the metal, and the mass of the metal. So your task is to calculate the specific heat of our cadmium metal.
So at this point, go ahead and put the data in your data table if you haven't already. And please put units with all the numbers too. I'm sure you were going to anyway, but just as a friendly reminder. Now, as far as calculations, you can see in the results table down there. So number 2 is what we're going to do now. Calculate the specific heat of the metal. Show your calculations. the first calculation I want you to do is to calculate Q for your water. And Q for your water is going to be equal to the mass of your water times the specific heat capacity of your water times the temperature change of your water.
Prof, can you say that again, please?
Sorry, what was that?
Can you say that again, please?
Yes. Oh, so if you look at the, see on the screen, the letter Q there? Q is going to equal the mass times the specific heat times the delta T, which is the change in temperature. So I want you to calculate that for your water.
The specific heat, is that just the final temperature of the water?
The specific
No.
heat, yeah, so go ahead, Michael.
I know so the final, the delta T is 25 minus 22. I get that.
Yep.
But where do we get the specific heat?
That's the 4.184.
Oh, gotcha.
Yeah.
That's on our conversion. Gotcha.
Does anybody have a number for, and a set of units for the Q, which is the heat absorbed by the water?
1255.2.
Lovely. And Anna, thank you as well. 1255 or 1255.2 is good. What are the units on that, though? Anybody can chime in.
Grams, no.
Joules
yeah,
over
joules.
grams
Yeah.
Celsius.
It's just joules.
Joules.
Yeah, because so the 4.184 has joules per gram degree Celsius, but you're multiplying it times grams and by degrees Celsius. And just so you know, I will accept either 1255 or 1255.2. Either one is fine. Now, if you're looking at your results table, so the heat given off by the metal is the exact same number as the heat absorbed by the water, except the sign is changed. So go ahead and change the sign on your 1255 to make it negative and write it in the heat given off by metal. And I know it even says it must be negative. And the reason we do that is to just sort of drive home the point that in this calculation, we are assuming that all the energy that's taken in by the water, taken in by the water, that's why that's positive, is given off by the metal. That's why the heat given off by the metal is negative. Something we've been saying all along, but for me, what I love about this lab, especially when we do it in person, is we get to experience these kinds of things. Now, go ahead and calculate Q of the metal, and you'll use the exact same expression. Q of your metal equals the mass of the metal times the specific heat of your metal times the temperature change of your metal, where the only thing that you don't know is the specific heat of your metal. Because you know the mass, you know the Q, which is minus 1255. And yes, your temperature change will be negative. And can somebody who hasn't already answered tell me what they get for the specific heat capacity of the cadmium? And as a hint, it will be less than 1. I'm happy to answer questions about it too.
I got 0.284.
Right on. Good job. 0.284. That's the number, and the units will be exactly the same units as the specific heat capacity of the water. So make sure you add in your units as well. And thank you. Sorry I didn't see who that was. And what I'm looking for in your calculations, where it says show your calculations, is you should have a calculation for your Q of your water, and you should have a calculation for the specific heat capacity of your metal with all the numbers and for the equations. Yeah, you don't have to show your solving process, just have the numbers. Any questions about this one before we move on? Hearing none, then we'll continue. And yeah, so I'm going to stop the video there and then create another video for the second part in case anybody